Hello everyone, so we've done a lot of momentum and all that kind of fun. We're now going to move back onto something that might be familiar, and we're going to deal with pressure. Okay, and to start with, I want you to consider these two creatures, this one and this one. They're the only two that are on this picture, so let's consider them. One of them, the top one, was voted, I think back in like 2014 or something ridiculous like that. It was voted as the ugliest creature. And it's called the blobfish. However, it also looks like exactly like this one in the bottom. These images are both of what we call the blobfish. Now, the reason that it looks like this top one, the reason for this is this top one is one that's been caught and taken up to the surface. How far does it normally live? Well, if you are sort of here, living on the land, the blobfish is around about somewhere around about 1,000 meters down. And at that depth, the pressure that it experiences is a lot greater than what you experience. We'll come back to exactly how you experience what you experience, but you experience, I'll just define pressure to start with. So as a recap from year 9, hopefully you remember that pressure is a measure of how concentrated a force is. Okay, and it's measured in newtons per square meter or pascals. You can measure it in newtons per centimeter squared and whatever, but if you're dealing with newtons per square meter, it's equivalent to a pascal. Now, many things, as you might remember from year 9, it's quite straightforward to get the pressure of a solid at the bottom of a solid. So what you do is you sort of like you have your object, stick it on a balance to get the to stick it on a balance to get the mass of it, and then you would do okay. So I'd do so the pressure at the bottom, so sort of here, comes from the weight. So the pressure is equal to the weight of the object divided by the area of the base. Now, you experience on a day-to-day basis, you experience an air pressure. Okay, you experience an air pressure of around about 100,000 pascals, which is actually quite a big number. You don't notice it though, because you've evolved based on a planet that has that air pressure. Where's that air pressure coming from? Well, it's coming from that weight of all the atmosphere that's above you. Okay, there's around about 50 miles of it. So 50 miles of air pushing down on you, essentially, is generating a pressure of around 100,000 pascals. That's air pressure. Now, what we want to do, though, is think, well, what's the air pressure where the blobfish normally lives? How big is it? You've got to remember, it's already got the 100,000. The 100,000 of the air, because the air is sitting on top of it as well, but it's also added 1,000 meters of water. Now, 1,000 meters, or a kilometer, is a lot less than 50 miles, which is around about 80 kilometers. So you do have a lot of air and then a smallish amount of water. But what does that water generate? Well, let's think about how we can solve that problem. So let's think about pressure due to a liquid. If we have a little column, and I'm going to go to blue. I'm going to design a column and I could get the ruler implement out and draw some straight lines, but I can't. Now this has become a weird optical illusion. I don't know if it has for you at all. So I've got this column of water. And let's not make it very deep. Let's make it 5 meters. Okay, and let's say that it's been filled and it's 2 meters that way, 2 meters that way. So I've got essentially a cuboid, not a cube, of 5 by 2 by 2. And I'm going to tell you something about water. The density of water is equal to 1,000 kilograms per cubic meter. Remember that density is equal to mass over volume. So the question becomes, okay, I need to work out the weight of this water, and I therefore need to think about how much weight is sitting upon this 2 by 2 kind of area. And that is going to give me the pressure at the bottom of that column. So let's think, how can I work out so what I'm after is the weight of the column of water. So I need to work out the weight. And I do that by using mass times gravity. But I don't know the mass yet. So before I can do that, I need to know the mass. And the mass is, thinking about how this equation is written, is density times volume. But I don't know the volume yet. I need to work out the volume, as that is the area of the base times the height of the column. But that's nice. These are all numbers that are there. I just have to go back and work it sort of backwards. So let's switch to red. Let's work this backwards. Well, I know the height of my column. It's 5. And I know the area of the box. It's 2 times 2. Well, it's 4. So I get that. That gives me a volume of 20 meters cubed. So that's nice. I've got 20 meters cubed. So I can take that. And I missed. So let's try that one again. So I take that. I go, oh, I know 20 meters cubed. That's there. Well, I know the density because I've been told it. It's 1,000. So I've got my mass. So my mass must equal 20,000 meters cubed. I'm just going to put this back here so that's on the notes. That's nice. Well, I know my mass. I can then put that into that bit there. So I can go, my weight is now it's 20,000 times gravity, which is 10. Oh, look, and that equals that. So I've got 200,000 newtons. That's the weight of that column of water. That's quite a lot of water, really. That's a big weight. Well, I've now got my weight. Oh, look, and pressure is weight over the area that I'm exerting it over. I'm exerting 200,000 newtons of force over an area of 4 square meters. So I can say, okay, so my pressure is equal to force over area. So I've got 200,000 over 4, and I get 50,000 pascals. And that is a big number. Remember, I mean, that is 5 meters of depth, and that's like half of what I'm experiencing due to the 50 miles of air above me. So that's only 5 meters. Oh my goodness, this is because water is so much more dense than a gas. So we end up with this big number for just 5 meters. We've got to go 1,000 meters down. Ugh, that's scary. But before we do that, we can actually think about, is there an easier way of doing this equation? And one of the nice things about it is, if you notice, when we were here, we multiplied by the area of the box. And when we were here, or the area of the base, sorry, and when we were here, we divided by the area of the base. So actually, we can work this through, and instead of leaving it putting numbers in, let's just leave it as sort of symbols and see what we end up with. We started by saying we want to know the volume, which we got from doing the area times the height of the column. And we therefore wanted to take that, and we therefore wanted to work out the mass, which was equal to the volume, area times height, times the density. So we had area times height times density, that weird little rho symbol. We then wanted the weight, which is the mass times gravity. So if we go there, we get the area times the height times the density times by the strength of gravity. Wonderful. And what we finally want to do is we take the weight and divide it by the area. So we get that the pressure is equal to the is equal to the force or the weight over the area. So that equals the area times the height times the density times the strength of gravity over the area. And look at the fun. I'm so delighted by this. I'm using the Galaxy pen. There's an area on the top, area on the bottom, which means bye-bye. You get to go away, and you get to go away. Because you're on the top and bottom of this equation, so we can lose you. And there we go. This is a wonderful shorthand for what the pressure is at the depth under a liquid. So this gives us the equation we kind of need to know. So the pressure due to a liquid increases with, well, the first thing is the height of liquid above. The second thing is the density of the liquid. And the third thing is the strength of gravity. Now, if you dive down you go swimming and you dive down, well, generally the density of the liquid in the ocean doesn't really change very much. Like certainly not anywhere near as the level of 1,000. It doesn't change great much as you go down. The strength of gravity on the Earth doesn't really change as you dive down. So the only thing you can really fluctuate is this height of liquid above. As you dive down, you experience greater pressure. And so let's think about what the blobfish is experiencing. So if we say at a depth of 1,000 meters, the blobfish is experiencing a pressure water of, so pressure is equal to how have I written it? Just height times density times gravity. So that equals height is 1,000, density is also 1,000, gravity is 10. Well, that equals 10 million pascals. And that is why the blobfish looks so different when you take it to the surface. It normally, that is not what I intended to do. It will normally, its whole evolution has been designed to deal in this kind of weird area, experiencing about 10, 1, 2, 3, 4, 5, 6 pascals, 10 million pascals. And instead we've taken it to just 100,000 pascals. We've reduced the pressure on it by a factor of 100. And that reduction in pressure, from going from 10 million to 100,000, is such a giant thing that this entire body of this thing, which is designed to deal with this huge pressure that's coming in on it, all this pressure. So it's designed essentially with a sort of inherent springiness that is constantly, that is a terrible arrow, is pushing back. But if you take it to the surface, you remove that outward pressure. So you remove the inward pressure from the water. You've only got the outward pressure that's coming in from its own design, like how it's evolved to exist in that experience, and so it just blobs out and becomes like as we see. And that is how we deal with pressure from liquids. Now there is a little addendum to this, which is that actually this isn't the final answer of the pressure that the blobfish is experiencing, because it is still experiencing this 100,000. Small enough to say, but the total pressure, if we want it to be really clear, would be 10,100,000 pascals. But in truth, that 100,000 pascals isn't having a massive impact compared to the overall 10 million. It's mostly about the water, not about the air. Now, anyway, what that actually ends up meaning is that for every 10 meters of water, you're increasing the pressure by about one atmosphere. So 50 miles of air, 10 meters of water. But this equation is how we work it out. It's quite nice.